Okay, so can you give a 1-minute intro about like who you are, what you're interviewing for, or anything you want to share?
Yeah, hey, I'm a sophomore at Northeastern. I was here on this channel a couple of weeks ago interviewing with Citadel. Did not get that one. Currently interviewing with 2 Sigma for software engineering internships. Yeah, I code in Python. Hopefully, I'm not that rusty at this. We'll see if hopefully I can do better than my first DSA interview here on the channel.
Okay, yeah. Yeah, how did you, I don't even remember. How did you do? It's been
You
a
gave me a
while.
lean hire.
A lean hire, okay.
I did not deserve the lean hire. I should have failed
Okay,
that one.
okay. Okay, we'll see how this goes. All right. Okay, so for the first one, so basically you're trying to calculate a sum of a subarray multiplied by the min value in the array. And you're trying to maximize this. So basically return maximum value here. So let me just give you an example. So in the first, let's say of this. So the best subarray to pick would actually be this, because you would get 2 times, what is it, 7? So you get 14. So this would be like the best subarray you can pick, and basically you just want to maximize this value, and all you have to do is return the maximum value you can possibly get. Feel free to ask me anything you want to if that's not clear.
Subarray is contiguous, right? So it's like 2, 3, 2, not like you can't just get like 3, 1. Okay, yeah, okay. Sure. There are other negative numbers on this.
Let's see. Let's say there's no negative numbers.
No negative numbers. No zeros.
No. We'll just say it's one and higher.
Okay. Okay, 1 and higher. Are we guaranteed to have like at least one number in here?
Yes.
Okay. There's a world where you just like, calculate every subarray and it's like really slow. It takes what, like something like n factorial time to calculate every permutation of subarray, something of the sort. Anyways, that's
So why would it be
inconvenient.
factorial if they're contiguous?
Oh, actually, you're right. This is contiguous. Sorry, forgot that. Yeah. N squared if we're contiguous, I believe. That seems about right. We could probably do better than that. So what we can do instead, it's just contiguous. Okay. Then an option for us is, I wonder, okay. Currently, my thought is, if we ever see like something like two-pointer approach, where if we ever see a number less than our current min value, it's never going to be good to have that. Wait, no, that doesn't sound right. If we see a number less than our min value, we could probably do something. Another option is, I'm not sure what we could do if we see a number smaller than our min value. I guess let me see if I can. Well, let me walk through this example first, and then by hand, and see how I would like do it myself, and then figure out, what a good strategy is for this, right? So if we start our subarray like here, or no, let's start small subarray first. Start at just 1. We have like min value of 1, sum of 1, right? Then we move our second point over. We see a 2. Our min's still 1. Our sum is now 2. Now we move over. However, so we get total of 2. However, a different thing we could do is just include the 2. Now our min is 2. Sum is sum is 3. Total is 3. Yeah, if we did 1, 2. Whoops. Now if we only take the 2 though, our min is now 2, our sum is now 2, our total is 4. We have a greater total. Now we have to bring up the question, is it ever worthwhile to keep that min value around? Does it ever make sense for us to be like, okay, having this min value, it is actually providing, some amount of assistance.
Mm-hmm.
So perhaps the way we could do this is we keep track of min values. So, oh wait, yeah, maybe okay. I'm not sure if this makes sense yet. I'm still trying to think through this. But if we keep track of like an array, and it's like, if we keep track of min so far, no. Where am I going with this? Min value 2, sum 2. Is there ever a world where we want this 1? Because I'm thinking like if we had like 1, 1, 1 in here, right?
Mm-hmm.
Then we would actually need to keep like all of these ones. Because now if we had like, go further in list, and it's if we pick like all of these ones until like the 2, we have something greater than if we just picked a 2, even though the min value is still small.
Yeah, I mean,
even
you
though
can
we
have an
could get
extreme
this
case
thing,
if you have like a million ones and a 2, right? You'd obviously want to have the
exactly.
ones. Yeah.
So maybe what we could do is just keep track of for every min value in this, for everything that includes the min value, or okay, what are my thoughts? For every value in this, we can keep track of, well, if we include this value, what is the maximum sum we can get? And to do that, what is it? We're something along the lines of DP minimum sum, maximum sum subarray, something of the sort, where we keep track of like, here's at any given point, what is our maximum sum we can hit if we, well, I guess perhaps what makes sense is like if we end at this value for any given value in this array, if we end like here or here, what's the maximum sum, and what's the min value? Then on the next number, we can choose, okay, from this previous thing, if we took that minimum sum, if we added this next number to the sum and then consider the min value, where do we get now? The problem is I think we'd have to track a couple of different numbers, I guess, right? Because sum and the min value are going to be, there's up to like n different numbers for the min value, right? And I guess the idea would be like, we don't actually know where we're starting.
Right.
I think I am kind of talking in circles. I don't think I'm really getting too much anywhere. I might just code up the n squared solution, take a look at it and go, okay, where can we speed up the process?
So I think we don't need to code the n squared because that's very straightforward, right? Like you just have 2 loops and you track a min and a sum. So I guess to give you a hint, so you're thinking of like these 2-pointer arrays, right? And like, how do I keep a value and how do I not? What if you start thinking of a problem in terms of what's the min value in the array? Like, does that help you at all?
So we can know the min value up to a point pretty easily. Oh, I guess. Oh, okay.
Like if you just pick a number and you say this is the min value, what's the array? Can you do that?
Yes. Okay. No. Okay. I see what you mean. So basically, for each value, we could just say like, for the min value in the array, it's like this is 1. If we have the min value, we can take the rest of the array. Then for the second min value, which is 2, we can have everything except for the 1s. Because if we had a 1, then we would therefore already have a bigger sum by adding everything up. Okay, so now we want to figure out, okay, for any given value in this thing, what's the biggest array in here that does not contain anything smaller than this value? Because
so how would you pre-compute everything you need efficiently?
Yes. To know what the smallest thing up to this, probably 2 pointers, I guess. So like if we had this 1, right? I guess this is. I want to count the occurrences of each number in the array, right? Then for the 1, it's trivial. This is the smallest value in here. We take the full thing. But for the 2, it's like slightly less trivial. We have like a pointer here at the left end. We have a pointer at the right end. Then for the 2, let's oh, okay, hold on. No, I was thinking about like if we could do a 2-pointer where we like move these in until we passed all the 1s on this half of the array. Except that doesn't quite work because we don't actually know how many of 1s there are before versus after this any given 2. Well, yeah, we do. Yeah, we do. Wait, we know exactly how many 1s there are. Because we just have to go left pointer first. So we go left pointer all the way up to this 2. We count how many 1s we've seen so far at this point. Then, like, so we've seen 3 1s up before this 2. We know there's 5 1s total. We move this right pointer inwards. We passed 2 more 1s. We finished every single 1 in this array. And now we took a look at the sum between left point, right point. And of course, we're going to be doing pre-computing the sum as we move these pointers inwards.
Okay.
That was a lot of words.
How would this work for a generic, like there's a bunch of different numbers?
Yeah. So like, so we know the occurrences of every number of the way, just counter up, right? So like for this given one where it's got like 1, there's 5 of those, there's 2 of those, 3, there's 1 of those, right? So for the 1, we just take the sum of the entire array. We move this left pointer to the start, we move the right pointer to the end, right? And then for 2s, let's first move the left pointer inwards until we hit. Oh, actually, because we don't know if we're using the first 2 or the last 2 or any 2 in between, huh? Because there's multiple ways we could use that too. Perhaps what we need to do is
the other question is, so you have these pointers, right? But how do you know which one to move? Like,
yeah, because I was kind of like working on the, and I thought that's like we're going to pick a number first, like this first 2, right? And then we're going to move left all the way in to this 2. Then we move the right all the way until we've counted all the 1s. We've passed every single 1, except there's no guarantee that there's no like 1 there.
Right.
And then the second 2 is like, more important than the first 1.
Exactly.
Except, and I don't think there's a way where we just like, look at every single iteration, every single like 2 in the array. That seems kind of awkward to do. Unless maybe, no, actually, yeah, that doesn't make sense there.
Yeah, like you might not be able to keep all the 2s. You might only be able to keep a couple, so you don't know which way to shrink because you don't know.
Yeah.
Yeah.
You don't know where to center the 2 pointers.
And you don't know which one's better. Like there might be like a bunch of 2s here, right? And there might be a bunch of 2s here. And like, how do you know which one's better? With this, you don't really know.
Yes. Yeah, that's right. So I guess what is it? We pre-compute some kind of DP maybe then. Let's say let's
so let's pick a number. Like for an element, like let's say we're here.
Yeah.
We want to know, like, I want to pick an array with this element being the min. And you kind of said that, like, that means I can't have anything bigger on either side, right?
Yeah, we could like pick, some number and then just like expand outwards until we like see the min, until we see a number smaller, right? And that's an option.
But you can't do that for every number because that's unsquared. But yeah, basically if I say like this is the min, then this needs to be my answer for this being the min and so on, right?
Yeah, that makes sense. So maybe if we pick a number, we like, left pointer, right pointer, we expand out until we see number smaller. But then we already know the endpoints of this thing, right? We know that, like, if we expand it outwards here, we went until there-ish.
Mhm.
We've already included all of these somewhere for every 2, I guess. Then if we see a 3, so we don't have to like recompute this, I guess is kind of the idea of like for each 2, we don't have to recompute that like, stretch of 2s. And that's worst case, I think that's still ends. No, I think that is actually might actually get to n, because I'm thinking like what's worst case look like, right? And something like this, we see these ones, we count all those we count these 2, we count everything in 1s. Then we see 2s. We count like this stretch of 2s, then this 2, then those 2s. Oh, I guess that might
Yeah,
actually
but those
still be
2s might not be 2s.
Yeah.
There's other stuff between them.
Yeah. But if there's other stuff in between them, like this 1, we don't count that 1. So it's like, we don't have to recompute the entire like list of 2s, right? It's like we grab these 2s. We don't have to like look beyond that since we're already boxed in by 1s. But if perhaps there's a way to pre-compute, you can pre-compute for like each number, and I don't think that hits n squared. I think it's slightly less than n squared. In worst case,
I think it will still be roughly n squared, because like if you have 1s and 2s and whatever, for 1s you're gonna take the whole thing. Then for 2s you're gonna take the whole thing or most of it, and then for like 3s you'll take most of it again. So it might go down by like half every time, worst case, but it will still be like
that's still
pretty big. So basically, what you want to know is like for a number, you want to figure out like what's the boundary for that number. So is there something you could compute that would help you? Like basically, you want to be like, if I'm here, I need to know like what's the boundary of the array with this being the min. And is there something you can pre-compute with that you can reuse and you can pre-compute efficiently?
Yeah, sure. We could figure out like for each number, we could probably pre-compute like what for any given 2 in the any given 2 in any given position in the array, we can pre-compute like what's the first occurrence of a 1 on left versus right. Does this save it as time?
So can you think of something more generic, like not for a given 2, but
for any given number, we could pre-compute like what's the first occurrence of a number smaller than this number.
Mm-hmm. And how long does that take? So like, let's say if I want to know like what's the first occurrence of a number that's smaller than this number on the right, like can I do all this quickly?
Sure, I guess. Yeah, I guess we'd look at I guess we might want to just keep track of like okay. So like I guess for like, yeah, hold on. Let me put my thoughts together. For 1s, right, we'd have like 0, 1, etc. Then for 2s, we look at like the 1s. Oh wait, this for 1s it'd just be for 1s it wouldn't be. We'd have nothing because there's nothing smaller than 1s. But for 2s, I guess we'd have like at index 0, there's for indexes without a 2, let's just say -1, I suppose. But this first 2, we see the first element on the left that's smaller is at index 1. And then for the second 2, since we're still looking at 2, we can just reuse the previous element, etc. Now we see the next 1. This is a -1, right? Now this next 2, we see, sure, we have some element, we have -1 right before us. So the element that oh wait, this is not 1. This is 1. Oh, wait, no, this is still 1. So the first element that is smaller than the 2 is whatever this index was. I think this is like 5 or something, right? And then this 3, this is greater than 2. Let's call this like inf, because it's greater than the 2. We see a 1, let's stick a -1 there. 2, what's this, like 7, et cetera, et cetera. That's for the left side coming towards the right. Now for the right side coming towards the left, we do the same exact thing. Then for 3s, we can just look at the graph of 2s and check where, if we're at like this 3, this is index like 6, we'll look at like the index of like 2s. And then this, if this is like not infinite, then it's whatever this index was, right? So we've got like ... like all the way up to like here. And then it's like index 6, I believe, for this 3 right here in the middle. Because for anything greater, we'll store it as infinite. Then for any number that's not infinite, that's a number smaller than this. And this is for like 3s, and this is for like 2s.
So why does it matter for like you're kind of solving a different problem for every number? Like all I care about is like for a number, where is the number that's like, let's say you're checking the right. You're saying like, where's the closest number that's bigger than that number, right?
Yeah.
So if that's literally the problem of like, imagine you're given an array of nums, give me back an array of index of first number greater than each. Like why? Like why do you have to like for 1s? Why do you have to look for 2s and 3? You know, it's like why can't you just have a generic? It's just like I have some numbers. If I have a number that's bigger than those numbers, then I like put that there. Does that make sense?
Oh, can you say that again?
Yeah. So let's say I have like, for example, 1, 2, 3, 4, and right, maybe you initialize this with whatever null or infinity or something, right?
Yeah, sure.
Let's call this like infinity. So basically, for this first one, there's nothing bigger, or there's nothing yet. And now this one is bigger than this one. So then for this one, you would just write like this is index 1. Now this one is bigger than this one, and this is index 2. And for this number, once I found a number that's bigger than my number, like anything to the right of this is irrelevant, right? Because like I need the closest one. Same thing here and here, right? So this would be like 3, 4, whatever this is. I guess this would technically be like, 1, 2, 3, and then this would be like infinity still. So as long as I get a number that's bigger than like stuff I have, I can start getting rid of those things. And think about how you'd want to store those numbers, right? I'm trying to find a number that's bigger than my numbers. So I'm never going to store numbers like this, because this 2 would already have like been bigger than the 1, and so on. And this 3's already been bigger than those, so and so on. So kind of, instead of trying to figure out for 1, I look for 2s, for 2, I look for 3s, like what's a generic solution you can have that just solves this problem? Does that make sense?
I missed the second part. So like, okay, from what I understand, okay, so we've got this 1, 2, 3, 4. What happens if you like see another 2, right? Do we just like look at like, we look for the first 2 we've seen, or like first?
Okay, so basically, let's see. So for these 3, like let me just copy this. So for these 3, these are already done, right? I found something that's better. Now I have a 4. Is 2 greater than 4? No. So then I just like leave it as is, and then I keep going. Maybe I've hit a 5 here, and now the 5 is greater than the 2 and is greater than the 4. So we'll like get rid of those and so on. So do you kind of see a data structure you could use to do this easily?
Yeah, it's a monotonic stack.
Right.
I'm currently trying to think about like how we would use that to like keep track of monotonic stack, but this is keeping track of the greatest number we've seen up to this point, right?
So monotonic stack is either increasing or decreasing. So which way does it make sense to store here?
Decreasing, I suppose. We want to know what the smallest number up to this point is. And then how many numbers before that. And then as we add in numbers that are greater, we just leave it in No.
Yeah, so like in this example, this
yeah.
5 will override the 2 and the 4, and it will just be like this. So it's gonna stay decreasing, and then all you have to do is just compare to the end, right? And then like if it's not bigger than the end, then like it's not bigger than anything because you're fine. Like monotonic decreasing is going to be like this or whatever, right? So if I have a number like 1, if it's not bigger than this, it's not bigger than anything, and then I just like add it on. Does that make sense?
You add it on, and then okay, so we add that on to the end, and that can, we know from this, like, what is it? The I mean, that's telling us like what the greatest number before this point is. But like
it's telling us what's the first number to the right of my number that's bigger than my number, right? Because as you pop off the stack, like in this example, as you pop off the stack, like as you pop the 1, you're basically saying 2 is bigger than 1. So I could store the index of the 2. 3 is bigger than 2, so I could store like this and like this. This will have infinity, and this will have nothing, infinity as well. So basically, I know that like the earliest number that's bigger than 1 is at index 1. The earliest number that's bigger than 2 is at index 2, and so on. And if I have that in both directions, then I know like the length of my subarray, where this is the min. Does that make sense?
Oh, yeah. Okay. So the biggest number, yeah. Okay. So the biggest number. Wait, you're storing indices in here.
Yeah, you're storing indices. So this is basically like index of right number that's bigger than this number, or infinity or whatever if nothing exists.
Right number that's bigger than this number. At index.
Or I guess you'd want smaller because you want it the min, but yeah.
Smallest number.
Idea. Yeah.
Smallest number, that's
index of like right number, index of the closest number that's smaller than this one on the right, right? Because in order for 1 to be the smallest, there can't be anything less than 1 in my array.
Yes.
So basically what I'm showing you here is like this would be if you keep the max, but if you did the min, it would
we want to keep the min.
Yeah.
So it'd be like so biggest index smaller than 1 starting with infinity, then we see a 2. We see that this is what, larger, so we'd want to pop from this. Now we have a 2 in here.
I think in this case, because you want the number to the right that's smaller, I think actually all of these would be infinity because there's nothing smaller. Actually, sorry. These 4 would be infinity in this case, right? Because there's nothing smaller. Or it would be like infinity, infinity. 3 and 4 actually do have a number. So this would be like 4, 4, infinity. This would be the answer for like index of the next element that's smaller. Does that make sense?
Yeah. So we figure out the next element that's smaller. Yep, that makes sense.
So it's just the other way. Yeah.
Yeah. Okay. So like going through this list, we'd like start with infinity. There's nothing. We'd start with infinity because there's nothing in there. Mm-hmm. Now we see a 2. There's still nothing. Well, I guess this is all initialized to infinity, so this isn't really like initialized to.
Yeah, you can make it whatever you want.
2. Yeah. We see a 3. We see 4. Now we see 2. Let's pop that. This is 2. This is smaller than we're looking at 2. This is smaller than this. Let's pop this. This is now index 4 there. We pop this 3 because it's also smaller. That's index 4 there. Now we see the 2. Let's just add this 2 on the end. That's infinity now. Okay, that stays infinity. Okay, now we know that. Now, then, we do the other side as well. We find the first element from the, we start doing the monotonic stack from the other side now. We start with like the 2 in there. Well, I guess this is index 5. We have to keep track of what. No, because it's. Yeah, we have to keep track of like whatever index we're looking at for these numbers as well. But like just two both for that, I suppose. We see this 2. Now we see this 4. This 4 is greater then the 2, which means that we need to 4 is greater than 2. We pop when it's lesser. So this is still increasing. That's fine. Then we see a 3. Well, we're looking at 3. This is smaller. Wait, no, hold on. We see the 3. We should keep this. This should not keep the 4 around because there's a 3. So I guess we'd pop the 4. It's like, what is it? We've got an infinity there. We're seeing the 3. We popped this one. Now this is like index 0, 1, 2, I guess. Now we add the 3 in, that's increasing still. We see the wait, hold on. 2 first, smallest before this 3. Oh, is this? I think the stack is supposed to be in the other direction because we want to know how many numbers we can get like greater. How many numbers there are that are greater than this, right? Or yeah, greater than this. Since the 2 is like less than this, we can't even have that 2 around. So we'd have to pop, I guess. We'd stick the 4 in there. Hold on. Still trying to wrap my head around this.
Yeah, so basically for a number, you need to know like this has to be the minimum in my subarray. So I need to figure out like what's the index to the left that's bigger and what's the index to the right that's bigger. And then that's like my boundaries, right?
Yeah,
Does that make sense?
Yep. And you use the mod attack stack to keep track of like here's the smallest. Here's the largest number up to this point. If we see a smaller number, we have to pop until we get all those out. From the right side, we also still have to add the smallest numbers in, or we have to add all the largest numbers in. Then if we see a smaller number than that, if we see a smaller number than the largest in the list, we have to pop it out. So we see a 2 first, then we see a larger number. Hold on. Because if we see a larger number, if we see a smaller number, we have to pop. So we do a 4 in there. Now we see a 3. 3, we have to pop out this 4 because now this 3 is smaller than that. So now this 4 gets index 2. Now we see another 2. Now we have to pop this out. Then this is like index 1. Then we see a 1. Now we have to pop both of those. And it's like 0, 0. And now from here we can calculate like what the largest is from. We know the biggest subarray that includes this 3 and 4 and also the 2s. So for this first one, we see infinity and 0 as the largest passes, smallest pass, largest on the right, or indices for the right versus left. I think if we see it infinite, that means we can go to the end of the right side. If we see a 0, well, I guess that means we can go to the end of the left side, I suppose. So that's like 1, you just add up everything. If we see the 2, then we go from 0. Oh, not including 0. If we see the 2, we can't actually include 0.
Yeah, so you probably don't want to store 0 as a default because
yeah. Except for this 1, it's like we're hitting, what is it? The 0th value. We can't include that.
So you can just think of a way to index things like you had infinity for the right.
-1.
You can, yeah, something like that.
Yeah, that makes more sense. So we just don't include this value. So we go from infinity to 0, not inclusive. Infinity to 0, inclusive, not inclusive. 4 to 1. So it's like 2 all the way to 1, not inclusive. And then we see 4 to 2. It's like, oh, this is not inclusive as well. 0, 1, 2, 3, 4. So it's 4 to 1 non-inclusive. So that's like
yeah, so 4 would just be the number 4 by itself.
Yeah, 4 to 2 non-inclusive is just index 3, which is this 4. Index 2 is infinity, infinity.
It
How do we
shouldn't
make
be
sense of that?
infinity, infinity, because there's a 1 that's smaller on the left, so you can't have that
Oh,
one.
that's right. This is 0, I suppose. Yeah, that makes sense. That's what yeah. So it's infinity to 0. So we go like, all the way from the end to not include 0. Okay.
And so one last question. So how would you, so you have these boundaries, right? How do you efficiently get these sums quickly?
Prefix sums, I suppose, right? Because we would know from like 4 to 1, I guess, already at 3. Then we hold on. We probably shouldn't have to use some kind of DP for this. There's probably some kind of you could probably prefix sum this from because this is increasing. We can just look at there's got to be a prefix sum solution. If not, you could always just like keep track of like 4 to no, that doesn't make sense. No, it has to be prefix sum then. So wait, from infinity to -1, that's everything. Infinity to 0, we've just gone up one number. So now we subtract the element 0. 3 is 4 to 1. So let's subtract the element of 4, subtract the element of 1. And that's so it's like whatever was at 2, we subtract the element 4, subtract the element 1. 4, we still have the same 4 there, so let's subtract the element at 2. And then versus 2, we've got infinity 0.
So when you say subtract, you basically say, so I get what you're doing. So you're basically saying take the entire total, subtract my big array, and then subtract the small array to like double subtract, so that part gets added back, something like that.
Yeah, something of the sort. Just like for this first one, right, we're adding in the full array, right? Then when we see this 2, we see this runs from like infinity to 0.
Right. So you basically want like this. You want like this bit, right?
Yeah. So basically, what we ended up doing was like we took out the last element. So let's just let's take whatever sub we found from 1, subtract the last element, then we move in. Now we see 4 to 1. Let's subtract the last element at 4 and subtract the element at 1. So it's like from like what was that?
Oh, I see. So you're subtracting. So like you're subtracting like the right part that's missing and the left part that's missing.
Yeah.
I see.
Something like that.
Something like
so then
that.
For 4, we get like we had this 3, 4 at like element 3. Now we've subtracted the element at 2. Now we just have 4. The problem is we hit this 2 again, where we hit infinity to 0. We could probably cache these, just like keep them all stored in a DP somewhere.
So what does caching do for you? Like if I say like what's the sum of one index to another, prefix sum gives that to you of 1 already, right?
Yeah, the problem is like we hit like this infinite to 0 again. We've got to like at 4 we've seen like 4 to 2. If we're hitting infinite to 0 again, well, we probably have calculated that already. Is that guaranteed? Might not be. If we see infinity to 0 at this 2, our prefix sum is looking at like 4 to 2, right? We're trying to find infinity to 0, which is like the full thing effectively. So prefix sum might not be able to get everything out of there.
So are you storing the prefix sum as a number or as an array?
I was thinking of that this as like so what we're actually storing in each of these, right, is like we want to know the sum of the biggest thing at this point, and also the min. So we'll have like some kind of array, right? And it's like we've got like sum comma min or whatever. And our actual prefix sum is just a number. Although maybe when you put it that way, maybe it makes more. But it's like, yes, we're keeping track of a number, but we also have like this kind of array at every index storing sum comma min, right?
So are you familiar with just like So basically, with the prefix sum, if you store as an array and you have 2 indices, you can just calculate that in O of 1, right?
Oh.
So.
Oh, yeah. Wait, yeah, you're right. I'm overcomplicating this way too much.
Yeah,
you're right. Hold on. Just prefix sum it. You sum up every element of the array, find the sum to that point. So it's like 1, 3, 6, 10, 12, etc., etc. Then we see like infinity to -1. So it's like 12, because that's the last element. So it's like element -1 minus element -1, because there's no 0. Element -1 minus element 0, element 4 minus R1, etc., etc.
Yeah.
Yeah, that's proper prefix sum. You're right. I was overcomplicating this for no reason whatsoever. Yep.
Okay. So what's going to be the full time and space for this?
Yeah, so computing these monotonic stack, that's O of n both ways. Then prefix sum O of n space. Then run through all n indices, look at the stack index, find the prefix sum calculation or whatever, do the prefix sum calculation there. O of n time. O of n space O of n time.
Yep. Okay. Okay. Do you want to try to get a solution?
Do I have time? Yeah, sure.
You have about 12 minutes. Let's see how far you can get. I think the coding is like not as hard as the figuring it out.
So. Yeah. I think monotonic stack just was not really thinking about that. Def, I don't know. Find min stacks something array as a list of int, and we are returning an int. Now let's see what do we want to do.
Okay.
Left, right, sum is inf. Let's say num elements is len array or something times num elements. Now right left. This isn't sums yet. This is mins. Left min. This is float inf. Times num elements. Okay. Now let's actually do the thing. First we need monotonic stack. Let's have a stack. Then for IDX in range len range num elements. Now, if not monotonic stack, let's just add this in. Monotonic stack dot append r at IBX. That seems about right. Now, else there's something in it. Else while monotonic stack of -1 is less than, or do I want less than or greater than? Monotonic stack, we want to know what's in the array. That is, we want to add it in if it is less than, pop if it's greater than. So while monotonic stack is -1 is greater than element RGX. So I don't have to keep calling this each and every time. Monostack element, while monotonic stack greater negative, the last element is greater than element. Let's pop that out. So now we do what am I actually storing in here? Wait, I am storing element, comma, index tuple, so I know where to find that element again. So we do store element, comma, IDX. Yeah, -1 0 text stack comma element, while as element the number at the last element is greater than element. Let's pop it out. Element pop idx is monotonic stack dot pop. Now left right min at popped idx. Let's have this be equal to the new index we just put in. If I have an off by 1, I'll take a look at it later. So we pop that out. Yeah, we pop that out. Put that at the index. Now, whatever we did, now we just have to add our new element index thing back in. Monotonic stack dot append element comma idx. Awesome. Now we add that back in. And now we should have left right min full of the first thing from. We start from the left side, and then if we ever see something greater than element, if we ever have, so we'll have something like 1, 2, 3, 4. We see a 2, and now we start popping it all into like pop that, and this is all the same. So now this is 4, 4 as we expect. That seems about right. Now for idx in range, elements -1, -1, -1. Element is an array idx if not monotonic stack dot append idx. So the same thing, just doing it backwards this time. Else monotonic stack like 1 0 is greater than element. Wait, is it just doing it backwards? Let me check this actually. So we start with 2 first, then we see a 4. This is greater. 3 is less than. We'll pop the 4 out. And now we'll pop the 4 out. The greatest thing past. Wait. 2, then 4. If we see the 4, do we need to pop them? Do we have to pop? Is my sign flipped? If we see the 4, the greatest thing to the right of here. The first thing smaller than this to the right of here. If we see the 4, then we should first thing to the right greater than this to the right of here. Or no. We already found that. To the left of here. Yeah, that makes sense. 4, then we see the 3, then we pop the 4. Yep, okay. Yep. So it is still we pop if the current element is greater than new element, we can still need to pop. Well, we don't actually even need this anymore. idx equals dot pop. Now right left min pop idx is do idx. Now we do monotonic stack append element idx. Great. Now prefix sum. Prefix sum is a stack. Or is yeah, that's fine. For idx in range for num in R. Per sum is 0. Per sum plus equals now we do prefix sum plus equal dot append person. That'll give us a prefix sum. That's a pretty solid list. Start from 0, goes up to n-1, gets all the numbers we need, all the prefix sums up to that point. That seems about right. Now, what do I need? I need to have now for each element in list, we look at monotonic stack, or we look at left, right, min, or left, right, min. I this is poor naming. But left, right, min is. Let me click comment. Leftmost point that array our IDX can hold such that what is it? Our IDX is the no leftmost point that first last element left of IDX smaller than our IDX, and then this is first element right of IDX smaller than IDX. Now,
Okay.
We've got monotonic stack. Now, for what I actually need, maximum is no, this is 0. That's fine. Now for IDX in range, elements. So now we do left, right, min minus right, left, min. No, other way around. Right, left, min minus left, right, min time, as in prefix sum of left, right, left, min, ID. Okay. So now we do, sure, let's call it current max, just to make this a little bit more readable. So we do R at DX. This is the actual minimum. Then we do what is it? Right, left, min at IDX minus no, this is prefix sum of right, left, min IDX minus prefix sum of left, right, min at IDX. Where prefix sum is a list, right? Left, right, min is a index. At index is a integer. So why am I getting a error?
I mean, you can have infinity, which I don't know how that works in Python, but like that probably doesn't work, right? Like if this doesn't get modified,
right.
You'll say at index infinity, which doesn't make sense.
Yeah, that's a good call. Let's just call this the last element in the list. That makes way more sense than infinity. And it kind of works out for what I'm trying to do anyways, I think. So last element in the list is actually going to be num elements. And then first element of this, -1. Left, right, min, index. Except we're not actually including the last element in this index. So I think I do have to do a -1. And then prefix sum, right, left index, +1 from left. Left, right is going to hold. Oh.
So prefix sum doesn't include this value, right? But if you have -1 here, that would be a bug. And it doesn't include it. So like if I have 0 here, it won't include 0. So this will actually, I think you need to make this. Well, I guess we can stop here and I can tell you because we're at time.
Yeah, I think I might off by 1 is somewhere. Yeah.
Yeah, so I think so basically it's like if I do a let's just stop here because we're at time anyway. But so if I do like right minus left, left is like the index of the last element that you want. And so I think if you had it as 0, then it would work because then it wouldn't include this thing, if that makes sense. So I think I think this needed to get set to 0, and then that would work. Because you would get rid of basically 0 means you're not including this left element. So if it was 0, you'd basically say like, okay, give me the whole thing minus this element, and then that would work, I think. If you want to include 0, then you would make the number bigger. Or let me think about that actually. So it's like, yeah, let me draw it real quick. I think you confused me. Okay.
Yeah.
So basically, the right index is included. The left index is not. So if I do this minus this, then it would just be this section. So if you did want to, yeah, I think it would be like, you would need to do -1 basically, which would be a bug. But you could just say like, if the left index is -1, then just give me the right, and that's it, and that would work. Does that make sense? I think that would be how you do it.
Right. Yeah, you have to do a check for that. Yep, that makes sense.
Yeah. And I think the infinity, I would do the same thing. I would just say like, if it's infinity, then just go up here and then just subtract 1. Yeah. Yeah, I think definitely what would have helped you here is breaking this down into like a few steps, because you could choose me and yourself, I think.
Yeah, I was kind of losing track of what.
So you could figure out like where's the right index, where's the left index, and then you can like break it down into separate a few steps to get the actual sum. But yeah,
I should have also had prefix sum have like a 0 on the left side.
That's one trick. Yeah, that's one trick you can do, so you never have the out of bounds. Yeah, it's personal preference. Yeah. So, yeah. So you would basically do like +1. Okay. So I think for this one, so for what it's worth, like I said, I think this would only be, I mean, I've never interviewed at 2 Sigma, but from what I heard and from people that did, you basically just get asked like super hard LeetCode stuff compared to like other companies.
Yeah.
So I would say that I would be pretty shocked if you were able to figure out the whole thing with like no hints for an intern. Because this is like a reasonably difficult problem. This is also why I really don't know why people are like, oh, I don't like DP or graph. I can easily give you a problem like this that's like, use a stack and that's it, right? There's no complicated data structure, but it's like reasonably hard anyway. And there's like a lot of stuff that you have to figure out. So I would say I gave you the hint of thinking of the min, and that got you somewhere, but I feel like it didn't give you enough. So like, I feel like every hint I gave you, I expected you to do more with, I guess, if that makes sense.
Yeah.
Where I had to give you a lot, and I feel like you were still kind of confused. Like, even after, like, I pretty much kind of told you like the entire algorithm, hint by hint. So I definitely would have like, I think if you recognize like, oh, hey, I can't, you did recognize a lot of this stuff, right? You're like, okay, I'm gonna do 2-pointer. Oh wait, it doesn't work. Okay, so maybe you want to think about it differently. Like, well, what if I need to just figure out the minimum, and then for the minimum, I just need to know like, yeah, basically this like, what's the next smaller element in a direction? That's like a medium problem, right? It's a pretty straightforward stack problem that I would expect you to figure out. So it's like, given an element, what's the index of the next smaller element in each direction? I like, once I kind of hinted you that it's this, I would expect you to get this like no problem. And I think you still like struggled a decent bit, so I definitely think you need to review just like
monotonic stacks. Yeah. I think I've done like 2 problems total on that. Yeah.
I mean, the thing is also with the monotonic stack, you don't really need to know. Like, it's one of those things where like you don't need to do a billion problems. You just need to understand a concept. It's like, okay, I have a stack of numbers. Anytime I have a number that's bigger than something, I need to pop off, or smaller, then I need to pop off those things. And like, basically the only question is like, should it be increasing or decreasing? I think you figured that out. But then, yeah, you definitely like confuse yourself a lot. And then also this prefix sum, you were kind of doing, you had this like weird solution, and I was like, what are you even doing here? Like, that was also like, that should also be like pretty straightforward, like how to get a prefix sum. And you should understand like, okay, I have 2 indices, I need to get a prefix sum. That's an O of 1, and I just like have an array. And I was like, what are you caching? It's already O of 1. I don't really understand. But I guess you had like the whole array, and you kept shrinking and shrinking and shrinking, and you were like, oh, now it's bigger, so I can't get it anymore. So like, I need to cache maybe. So you definitely like overcomplicated that by a decent amount.
Yeah.
And then let me see. You also had a decent amount of bugs, like even after like you knew the solution, you had a decent amount of bugs. So for example, here, this would get an index out of bounds because like your stack can just become empty, and then this would just be an error. So you needed to check. So
Yeah.
these two should have been combined. It should be like while this
Monotonic cycle.
and
Yeah, and yeah.
this, and then the else can just go away, and it would basically be like that. So you always append, and then you have the while, and yeah. And then definitely I was gonna say definitely work on your variable names, because I was like, you can confuse the hell out of me with this like left, right, min, right, left. Like I would have just said like, like right boundary. And this is like pretty clear, and like left boundary.
Oh, that is way better.
Right. And then you could just make maybe a comment of like not including this index or something. Not included, right? Like here, not included.
Yeah.
So I definitely think there is a like an art of, okay, you understand the algorithm, but like, can you code things that like make any sense? Can you break down a complicated problem into like multiple sections? Because I think this one is basically like 2 or 3 problems in one, but each one of those 2 or 3 is like a medium. Like they're not that hard, right? It's like calculate a number that's smaller, calculate a prefix sum, combine all that, and that's the problem. And for an intern, I definitely would give you a ton of hints, and that's totally fine. But I feel like for like a very competitive company, I feel like I gave you too many hints, and you just like weren't making enough progress with each one. And I was like not sure how to calibrate this thing, but I was going to give you 2 problems, but you were like moving a little bit too slow to give you another one. And I think for an intern, it's probably pretty fair to just give you 1. But regardless, I felt like you definitely were like confusing yourself. You were kind of stuck in a spot because you were having trouble understanding like what exactly do I need. Like you were writing these examples, and I don't know if you were like super sure how this was going to work, because it took you quite a long time to like figure it out, even though I felt like it was like straightforward-ish, especially when it gave you that many hints. So I definitely like, it's fine for me to give you hints, but I think you should do more with each hint. And so I feel like having done these interviews, I definitely feel like your stronger suit is the practical stuff. I feel like the practical stuff you did, like if I calibrated you versus other people, you did extremely well, because there wasn't like heavy DSA, and it was like, can you write stuff? Can you like add on to it? But I definitely think in the DSA, you kind of confuse yourself a bit. You take too long a bit, and a lot of the DSA stuff is you just got to move fast, or you just run out of time. And I think you mentioned, also like that other problem you had for Citadel, like it was like you did something, but it took a very long amount of time. So I definitely think you're like running into the same thing here, where it's like, I would expect you to move faster, given, like I said, a very competitive. Obviously, this would be like way beyond an intern for like most companies, but like a very competitive. Like I think for this kind of stuff, they're basically just looking for like, I don't know if like competitive programmer, but just like very very good at like algorithms, and like significantly better than average. So, yeah.
All right. Yeah, it sounds about right. That sounds good. I think I do have topics to review. I got to get a little bit more practice on that. Like I do need to review monotonic stacks and things to that. It's been a bit. Yeah, I guess I will. I don't know. I'll see you again if I make it past this one. We'll see if that happens.
Well, I think
all right.
I think if you have like one day, definitely review topics, but also I would work on small stuff, because like you only have one day, like naming, having a structured process that you don't confuse yourself, like all this kind of stuff. To make sure you're not just like going around in circles, and really trying to get things done a lot quicker than you are.
Yeah, taking the time to like write out like the actual process of like, here's all the things I'm gonna do, and like that kind of thing. Gotta work on that. But just kind of hard to figure out like how I want to space my time once like,
I mean, with one day it's kind of hard to space your time, but yeah.
No, I mean like in the interview, when I get like, when I get stuck on a problem, like just conceptually.
So I would say
like 20,
I would say like
minutes.
It depends on like, do you know the format? Do they tell you like, this is how many problems, this is how much time, and whatever?
I believe it is. Hold on, let me check. Okay. I believe it's like an hour actually.
Okay. I would very much like to know, like, and I would clarify this up front, like, are we doing 1 problem? Are we doing 2? Are there 4 parts? I think knowing how much there is to do gives you a nice way to time yourself. Because if you know there's like 4 problems, like, you basically have to rush through it, and if you don't get it, you don't get it, But if you know you have an hour for one, then you can kind of be like, okay, well, I have time. So definitely, I think clarifying that stuff up front, getting as much info as you can, is going to help you pace yourself. Because a lot of companies might just give you like 1 hard problem, but give you like an hour,
Yeah.
And then you can definitely be like, okay, I really need to know what's going on. I really need to break down all the like things. I really need to get a good thought process because I have the time, but I can't confuse myself and go nowhere. So things like that would definitely help you.
Yeah, that makes sense. But it's like, I don't know, you've seen me get into the spot where it's like, man, I've spent like 25, 30 minutes just like thinking about the problem, not even writing code. It's like, how do I like,
That's fine if you have an
this?
hour. That's fine if you have an hour.
I get, yeah. I guess if I have an hour, that is way more time than I would have like needed.
But like as far as like the thinking, not writing code, it's like you kind of notice you were going in a circle and you pointed out yourself. You're like, I'm doing this won't work. I'm doing this won't work. I'm doing this won't work. And for a lot of these problems, you kind of have to think outside the box, right? So the traditional way of thinking for this kind of problem is like, okay, so I probably have some kind of pointers and I like minimize some window because that's like most of these, like it's like, people are like contiguous sliding window, whatever.
Yeah.
So you kind of have to think more of like, okay, well that doesn't work because I can't shrink it. So like what other requirement can I have? And then you could think of like, okay, well, yeah, so I have to have them in because that's the only other thing I could do. And once you realize like, oh, if I know this is a min and I can get the boundaries and this is like a problem I know how to do, then I can do that and so on. So definitely you want to think of like what are multiple things I can do and try not to really put yourself in like tunnel vision extremely into some crazy category. I've seen people do that too, where they're like tunnel visioning so hard and I have to basically tell them like you're just going in the wrong direction. So I definitely try to explore different opportunities. If in like 10 minutes you're going nowhere, be like, is there something else? And then that depends on your interviewer. Like they might not give you hints. They might just be like, I just expect you to figure this out. But for what it's worth, I think for an intern, you're going to get asked easier than this. Like I think this was like pretty extreme. But still, the same concept applies. If you're going in the wrong direction, you need to learn to recognize it and kind of pull yourself out of that thing and like look for other stuff.
Think about other approaches. Yeah.
Yeah.
Kind of just hard for me to like think about, okay, here's an approach, here's different approach, here's,
I think that's where you really need to understand what constraints you need for an approach. So for the sliding window, you need to recognize like, oh, it won't work and here's why, because the sliding window doesn't work here. Or for that counter that you mentioned, it's like, it won't work because like, what if I have a group of twos here, a group of twos here? And so that's where the fundamental knowledge of DSA and like what algorithms work where and why not really helps. And a lot of people struggle where they just start guessing. They're like, oh, I use sliding window. I don't really know if it won't work. I'll just keep going in this direction until they tell me stop. So the more solid people understand like, oh, I can't do this because of this constraint that will make it break, or I can't do that because of this constraint, right? I think that's where like the really in-depth knowledge of DSA shows. These people can figure out their own edge cases. People can stop themselves without the interviewer having to be like, yeah, you're going down the wrong way. Because sometimes the interviewer will just sit there and be like, all right, time's up. Sorry. So
yeah. All right. Sounds good. Thank you.
Okay. Cool. Yeah, let me know how it goes. See ya.